First of all, I guess I should introduce myself. I'm Stephen Simmons. I work at JP Morgan in London. So I'm a Python developer working in the commodities trading business. And we have probably several thousand Python developers overall in JP Morgan. For much of the investment bank, the risk and trading systems are all written in Python. I work in a small team that runs gold and silver trading, precious metals trading. And so we sit with the traders. I have a small team in London. Other half of my team is in New York. And we build trading systems that manage hundreds of billions of dollars worth of trades, all in Python. And a part of that is using Pandas. And so from the work that I did there, wanting my own Pandas code to work more efficiently, I really wanted to dig inside Pandas to see how it worked, to see what made it run well. And the result is this tutorial session. So I did an earlier version of this talk at PyData in London in May earlier this year. So the slides have been updated with a few new slides added from that. If you have downloaded the sample data from my GitHub repo, that is actually a slightly larger data set than is used on the slides here. It matches what you would see in the Jupyter Notebook if you run that Jupyter Notebook, but I haven't gone through and changed some of the slides here. So when you see slight differences like that, just bear that in mind. So the goals for today is to take a look at Pandas, but starting from the beginning. So what's the foundation of Pandas? Built on Python, numpy for high-speed numerical calculations, plus the convenience of DataFrames from R. So we'll look at a bit of what's underneath Pandas, and then we'll go through quite a simple, straightforward example of analysing some sport statistics, but we'll do this in depth. And so the actual operations that we'll do will be quite straightforward. These will be the things that you do in your everyday work using Pandas for data analysis, but we will look deep inside the operations that are going on to see what actually happens from the perspective of the low-level Python and numpy objects deep inside Pandas. That will help us understand why Pandas uses the syntax that it does, and also it will give us some insights into which types of operations in Pandas are fast and which ones are slow. And as we'll see, there are differences of several orders of magnitude between them. The end result from all of this is that we'll all develop a pretty good intuition about what is efficient Pandas code. That's useful for any type of problem, but especially as you scale up problems bigger and bigger, then we really want to make sure we're doing things the right way. So those are the goals for today. We have 1 hour and 20 minutes remaining in the session, so that's a fair bit of time. So that means I'm able to stop, take questions if you have them. It helps to sort of break up the monotony of me talking all the time if you guys will put up your hand and ask me burning questions, or you see something on the slide that you don't understand or you think is a bit strange. We may not, or we're not able to go down every possible diversion that you may want to talk about, but please feel free to raise points that you think will be of general interest to everyone in the room. So to start, we'll put Pandas aside for one moment and do a comparison between plain Python and numpy. I guess I should really ask, how many people in the room here have used Pandas before? I'm getting most people have, because that's why you're here. If you haven't used Pandas before, then you can treat this as a bit of a gentle introduction to Pandas, and don't worry about aspects that are all new to you. How many people here have used numpy? That's great. In fact, which industries do people come from? How many people here are from financial services? From, I guess, pharmaceutical, or no one here? Okay, general tech, consumer tech, B2B tech. What other fields are people working in?
Government.
Government, oh, of course. I don't know, yeah. You can tell I'm not an American. Okay, so most people in the room have at least a basic familiarity with the ideas of numpy and why you might want to use it. So starting off here, on the left side of the screen is a way of visualizing a list of 1,000 elements, in this case, in Python. And the way that the objects are laid out in Python is that the list itself has a portion of the list object, the head of the list object, that tells Python what the type of the object is. So it has a pointer to a type object. It has a reference count, which keeps track of how many names in the Python namespace are pointing to that particular object. Every time there's another reference to that object, the reference count goes up. Every time a name goes out of scope and gets destroyed, the reference count goes down. When the reference count goes to 0, the object can be garbage collected and cleaned up. So that's in the head of the object. Also, for this list, we need to know how many elements are in the list, the size of the list, and then we have pointers to all of the individual elements in the list. So here, these are shown as the first eight numbers, and each of these in turn are normal Python objects. So these have the head with the pointer to the object type, and then a reference count for it. So that's what it looks like for Python. If we do the equivalent thing in numpy and create an array of 4-byte integers that's 1,000 elements long, then we end up with a header for the array as a whole, which has the same object pointer reference. It has a description that numpy uses to say what the shape of the array is, and then we have one block of memory that has all 1,000 elements in it. So you can see that's a far simpler representation of the list than for Python. What we've given up is some flexibility where these all have to be the same type. So they're all 4-byte integers.
Question before we move on.
Yep.
Does anyone know a way to introspect that on the REPL? Like, I don't off the top of my head know.
Yes. So these things down here will show you how to introspect that.
All right.
So that was a great question at the right time. So what I've done is I've defined a shortcut GSO to get the size of an object, a standard Python library function, and we can now compare the sizes of these basic Python objects. So a 0, integer 0, that's 24 bytes. So that would be the 8 bytes for the pointer to the object type, 8 bytes for the reference count, and then for the actual data for the number itself. So this is like a boxed object if you're in Java or some other managed language. If we take an empty list, then it takes 64 bytes, and then Python will tell us that the size of the list is 9,112 bytes. So you can go through and say, well, how many bytes is that per element? What this is actually missing is the size of the objects that are in the array themselves. And if they're all distinct objects, if they're not pointing to the same object, then we can add up their sizes individually, and we get 37,000 bytes. Now, at a very low level, Python identifies objects by ID, which is the memory location for it, and we can see where that is in memory. So that's the kind of Python sizes of these objects. We can do the same thing in numpy, and if we get the size of the numpy array, the empty array is 96 bytes. So numpy needs a little bit more information in the header of the array about its size and so on. And by introspecting the array object itself with item size, the number of bytes, we can see how that ties together. And so the total size of the array, which is returned by one of these calls, we don't need to add up the individual pieces, we get that and that together. Now, if we look a little bit further inside the array itself, there's also this array.data, which is the physical block of memory where that's stored. And that's really the C-level view of an array of 1,000 numbers. The shape and the strides of it is something that we will see numpy uses to figure out where the breaks in this block of memory are, to retrieve individual elements. So size is one thing, but what we are really concerned about at the end of the day is how fast these operations are. So one common thing to do with a list of numbers is to add them up. So we can take the standard Python function sum, pass in an iterable to that, and get the sum of it. If you're using IPython or Jupyter to do this, you can use the %time_it magic function, and that will do 3 trials of a certain number of runs and figure out the average running time. For these, in fact, we've extended the length of this array up to 1 million so that we can see a bigger difference. So for 1 million elements, the sum takes 10 milliseconds. If we do the same thing with the numpy array using the inbuilt numpy sum method, then it's 1.2 milliseconds. That's 10 times faster. And if we instead make the mistake of calling the standard Python function on the numpy array, not only is it much slower than the plain numpy function, which operates the tight loop entirely in C, it's also 15 times slower than the plain Python function. And the reason for that is the plain Python sum function expects all the objects that it's dealing with to be proper Python objects. So the iterator over this array needs to pull out each of these numbers from the array, form it into one of these Python integer objects, and then pass that off to the sum function. So that's a lot more overhead, and the total time for doing this is therefore 15 times slower than if we were just doing plain Python. So this is one of the first principles that we'll see over and over again today, is that the more work that needs to be done translating between these different representations of the objects leads to a big time penalty, big speed overhead. Now that's the one-dimensional case. The two-dimensional case, we can draw an array like that on the left. So in plain Python, we would have an array that contains each element is itself an array that has pointers to the individual numbers. On the numpy side, then we can do this by taking, say, one array a one-dimensional array, and then saying that we want to reshape it. And then that will give us a two-dimensional array. That's actually a really fast, really streamlined operation, because this second array in light blue is not recreating the block of memory for the data. All it's doing is having a slightly different structure describing the shape of the array, but then a pointer to the same block of memory. And this is something that numpy does really well over and over again. Wherever possible, it tries to reuse the same blocks of memory so you don't get an overhead from copying and recopying data unnecessarily. So let's take the second array we had from the previous slide and now add on to it a third array where we are being a little bit more sophisticated in how we're slicing that. So in this case, we have an array that starts at the third element, and then it has a step size of 3. So it's going through, so it would pick up the 3, the 6, then the 1 and the 4 and so on. If we look at that, we can use this a basic informational function, numpy.info, to see information on an array. And this tells us some interesting things. So the shapes of the array, from the two-dimensional case, you can see that that's a 3x8 array, and the strides tells numpy how many bytes to advance to move to the next element in that dimension. So for the two-dimensional array, in order to advance one more element row-wise, we need to advance 8 elements by 4 bytes or 32 bytes to move one row down in the array. Whereas to move one column in the array, we're moving just 4 bytes along, as we expect. The strides for the third array is 12, and that's because we are jumping over every third integer in this array. They're 4 bytes long, 3 fours are 12. An easy way to also see what's going on is this data pointer line here, which shows that the first two arrays are referring to exactly the same block of memory. The third array is referring to a block of memory, or is referring to the same memory, but its starting point is 12 bytes further on. So it's able to start at an offset inside that block of memory. And this is something that Pandas will use when we're getting subsets of a data table. It will use a very similar thing. Right. So one of the really flexible things about numpy is the many different ways that it can do indexing to pull out subsets of the array. On the previous slide, we saw a bit about how that works from referring to the start of the memory array and the strides and so on. And this slide is just a recap of the various syntaxes that we can use for doing that operation. So the most simple way of indexing from a numpy array is just to put in a single scalar to say that's the particular row in this case that we want. We want row number 1, the second row, and that will pull out a slice of the array, which is a subset of that block of memory. We can also do more sophisticated slicing, where we say we want all of the rows and just the first 4 columns, and that gives us a block like this array 3 here. And also as an index in there, we can pass in an array of integers, and that will let us select rows. Another way of specifying that is with a function called take, which achieves exactly the same result. And this is something that Pandas will use when, as we'll see when we get to indexing. So Pandas does indexing by figuring out which rows in a data frame it needs to take, and then using this take operation to retrieve them. Another way of getting out indexes from a numpy array is using a Boolean array. So here, let's say we want to get every third value trues. So we create an array that's true for the elements we want to keep and false for the ones we want not to keep. And then we can put that in as a subscript inside the array square brackets and pull out those columns. So these operations are very low-level, basic, highly optimized functions in NumPy, and they operate very, very fast with implementations that are all written in C. One of the other quite surprising things for some people that we can do is we can assign to a slice. So we can, rather than just pulling out a value here, we can then use it on the left-hand side of an expression and assign something into that. So here we can put -1 for all of the columns, for all the values that are multiples of 3, and that's the result. That's really neat. It can be quite useful if you say want to zero out some things in a NumPy array, and we can do exactly the same thing in Pandas. So what we've got to so far is enough of an introduction to NumPy to then be able to launch into how Pandas works. So let's just take a moment to look at where Pandas came from. So the origin of Pandas was in 2008 when Wes McKinney, AQR, an investment fund, really wanted something that would combine the flexibility and user-friendliness of DataFrames from R, but that was using Python, because Python is a much nicer syntax. It's a language that's great for prototyping, and also it's a language that has a really, really strong community, lots of great documentation, examples, tutorials, meetings like this that mean that it's a great language for businesses to base all their workflows on. Now, NumPy was...
Stephen, can I ask you a favor? I think a couple people in the back can't hear you very well. If you
Right.
could speak a little bit into the mic.
Yep. Is the mic actually on, or can the mic be...
Them, so if you can just project to the back of the room, and I'll check with
Yep. Can you hear this better now, or... Right. So do I need to hold this up to my mouth?
Try projecting first, and then roll.
Yep. Okay. And if you can't hear, just yell out or wave your arms or something at the back, and I'll talk a bit louder. I also have a cold at the moment, so I don't want my voice to give out halfway through. Okay. So the origins of Pandas were in AQR with Wes McKinney. He wanted to combine these three factors that would really make his daily work as an analyst much easier. Python is a great language, NumPy as a numerics library that a lot of people led, especially in the early days, by Travis Oliphant, really optimized for the sort of academic research case of numeric computing, plus some of the usable features of R. If we look into the top-level classes in Pandas, so you do import Pandas or import Pandas as PD, which is the usual idiom, and then do a PD dot and then a tab in IPython. This will show you what the top-level classes are. So I'm expecting that everyone who's used Pandas here is familiar with DataFrames and series, and perhaps time series as well, if you've been doing, if that's the type of work that you do. You're probably aware that there's an index and multi-index classes, and then some more esoteric types. And then as we go further down the list, you're probably less familiar with that. But really there's three, a relatively small number of high-level classes that we use. In addition, inside inside Pandas, there's a whole lot more specialized objects that actually make it work efficiently. Things like block managers, join units, blocks, and things like that. So who has heard of a block manager? One. Well, yes. Okay, so we will talk a bit about block managers. And so at the end of this talk, everyone will be putting their hands up about that, because block managers are actually what bridges the gap between numpy and pandas to make it all work. And I actually think it's, in one sense, it's testament to the user friendliness of pandas that have a room full of people using it and they don't know about block managers. But also it illustrates something else, and that is that pandas appears simple at the surface, but once you get underneath that, there's actually a lot there. So if you look at the number of methods on a data frame, you know, there's a lot. So there's 425, maybe 426 in the latest version of numpy that came out 5 days ago in 0.19.0. So there's a lot of stuff here, and in general, you won't use most of those. But one thing, the principle of Pandas, they try to make it easy so that everything is in the main namespace. You can hit tab at the REPL to get completions for things. That's great if you know what you want, but you can very easily find yourself in a morass of hundreds of different types of methods. Some of them are lower level, some of them are higher level, some of them are older ways of doing things, some of them are newer ways of doing things, and it can be quite confusing sometimes as to what's the right way to move forward. One of the results of this is that using Pandas often feels like it has a very bumpy learning curve. So when you start off, it's just like using Excel or anything else that you might have used. It reuses a lot of the common Python syntaxes, so it feels familiar. It's really easy to get started. But then as you get a little bit further into it, some of the operations that you expect you should be able to do are a little bit hard to figure out. And you're left scratching your head saying, how am I supposed to join these data frames together? Why am I getting a set with copy warning? Where is this coming from? And at least for me, it felt a bit like the learning curve was like this. I thought I knew how Pandas worked, and then I tried to do a little bit more, and it left me feeling really dumb because these things just didn't work. And then you look a little bit more into it, and something clicks. You figure that out. Maybe you figure out more about how indexes work, and then you can thank you. And, that's way better. So you then figure out how indexes work, and then you feel like your mastery has moved up to the next level. And then you start trying to do some things that are pushing against memory limits or speed limits or things like that. And then you feel like you need to take a couple of steps back and look deeper inside. So one of the aims of today's tutorial is to help give you a roadmap for navigating where these bumps are. Now, I don't expect that you will remember every little detail that we follow here, but it should give you the indications of where to go back to the Pandas documentation, look to the Pandas source code, and go into things in a little bit more detail to help get you over these hurdles. Okay, so now we're about to embark on our Pandas analysis. So the steps listed here are generic steps for doing any type of analytical task with Pandas. The basic steps: get our raw data and load it into a data frame so we can look at it, play around with it, see really what's there. That normally means we'd want to reformat columns, add indexes to it for looking things up and so on. And then take subsets of the data frame, do maybe some more specialized analysis or checks on that, and then produce some summary statistics by aggregating by different index fields, subtotaling things with groupby, and then doing some final processing for displaying results. So these are fairly basic steps, fairly generic. We're trying to keep this simple because the insight will come from what's happening underneath that. Now the starting point here is going to be Australian rules football. I guess there are no Australians in the room other than me. No? Fantastic. Has anyone ever seen Australian rules football on TV? Okay, so a couple. Okay.
Rugby?
No, definitely not. So Australian rules football started in the state of Victoria, which is one of the southern states in Australia, in the late 1800s. And in Melbourne, the first proper competition started in 1897. And so the competition in Australia now is, back then it was called the Victorian Football League, VFL. Now it's called the Australian Football League, AFL, has teams all around Australia. And they say in Melbourne especially that footy, AFL, is like the main religion there. To give you an idea of how important it is, last Saturday was the grand final for the 2016 series, and so the state of Victoria had a public holiday on the Thursday before, so there was a parade of all of the players, and then everyone took the Friday off as well. So it's a slightly sports-mad country, and Australian rules football is one of the most fanatical things about it. If you load this data set, the sample data set, you'll see it looks like this. And one of the, so this is a listing of all of the games that have ever been played since the start of the tournaments in 1897. One curious aspect is the scores here. And the scores are made up of three numbers. The first number is a number of goals, which is worth 6 points. The second number is something called behind, which is really something that's not quite a goal. And I'll show you a little video on that. But the total is the total number of points. So this is what Aussie rules football looks like. It's played with I guess a ball that's oval shaped, a bit like a football, what you would call a football. But the players, they're not wearing the players are not wearing body armour or anything like that. The whole aim of the game is to run fast, to jump high, catch the ball. If you catch the ball on the full, you can then take a free kick. And the aim is to kick the ball through the goals here. So there are 4 goal posts. If you get it through the middle 2, you get 6 points, and that's a goal. If your aim is not so good and you kick it, you miss the middle, but kick it between here or here, then that's a behind, and you get 1 point for that. This is a video from the Melbourne Cricket Ground, which is the playing surface for football there. It's about 120 yards long. It's pretty large, and it can fit 110,000 spectators. Now, let's see, this may play with sound, but it may not. Okay, so there's no sound here, but it shows how people run and catch the ball, and they can hand pass it by punching it and then kick it. And he's just kicked it 50 metres and got it through the 2 goals. The score was 1 point difference, and it was just before the end of the game, so everyone's gone mad. So that's what football looks like. That's what I call football, sometimes footy or AFL. So that's what we're talking about here.
The score there is the total score, or the...
So that's the total score in points, yeah. So the game has 4 quarters, so that's the end of the 4th quarter. The last seconds, so each quarter is half an hour long. Let's try and get this back. Right, try and get rid of this border. Okay, let's jump through. Okay, so the end result of all of the analysis we do, or from the player's perspective, the end result of a season of playing footy games is a premiership ladder. And here the teams are ranked by the number of wins, or by the number of points they've scored, and you get 4 points for a win, 2 for a draw and none for a loss. And then if teams are equal on points, then they get ranked by percentage, which is the ratio of points, as in six points for a goal, 1 for a behind, the ratio of points for and against. So what we're going to do over the next 40 minutes or so is to rebuild this table from the raw data there. So the first step in our analysis is loading this raw data into Pandas DataFrame, and one of the many things that Pandas makes easy is loading data in. So here, this is totally free-form text. Well, totally free-form text. And here we can load it in with just 1 line of code. I'm guessing most people have not used a read-in CSV data quite like this, with these number of odd features to it. There's a couple of things you can put in here. Skip a number of rows at the start to take out that heading at the top. The separator between columns can be a regular expression if the engine that it uses is Python. And we can also do things to parse dates properly into Python objects all in one go. So 1 line of code, that will read in our data frame. And if we display it from a REPL like IPython, we'll see something like this. So the different portions of the Pandas data frame I've highlighted in different colors. On the far left in red is the index, and you get that by doing .index on the data frame. And here it's a special type of object called a range index. And this is a bit like specifying in Python a range with a start, a stop, and a step. Exactly the same thing here. This whole index with 14,000 elements can be represented by just 3 numbers. And a lot of the time, we don't actually need to materialize index with all of these individual objects. Pandas can just use that directly. Along the top in yellow is the columns, which is a Pandas index object, which has the names of the columns. The game num, the date, the round, home team, and so on. Now, numpy if we go to numpy represented the types of objects in numpy arrays by a D type, a data type, and Pandas does the same thing, and we can get the data types of all of the columns of the array here, and also get the values of data in the array, which is in green. If we look at the values of the array, then what we get back is a numpy array where the different columns are of different types. So a bit like a rec array. So that seems quite straightforward, but that's not actually how it's stored under the hood. Yeah. Oh, sorry.
I was just going to ask real quick. I just noticed that, and I have this problem too, or observation too, that when you read in a date,
yeah,
you get a timestamp, which is the numpy.
Yeah.
It's a numpy timestamp, right?
Yeah.
Which is like way more precision.
Yeah, down to nanoseconds.
Are you
Yeah.
going to talk about what you might do to
No,
that representation?
things like that are kind of, I think, best answered by going off to Pandas documentation and looking at that.
Okay.
It's because there's a million features of Pandas, and I really want to focus on the structural things here. But you're right that it is storing it as I guess it's an 8-byte structure there. So what are some of the ways that we can select different columns of the data frame? So if we took the block in green that we got from doing .values, that took 35 milliseconds, which for a data set this big is not actually terribly impressive. Whereas if we get a data frame with 2 columns here with the round and the home score, the 2 that are highlighted in blue, that actually takes half a millisecond. So that's 70 times faster. So that looks a bit mystifying, isn't it? Such a big speed difference. Then if we got those same 2 columns, but we got them as individual columns, then actually they take just 2 microseconds each, which is amazingly fast. That's 250 times faster than the previous one. So that suggests there's something very different going on here. The last 2 examples here have, the first one is getting a series from a column, and then the second example is getting a data frame from the column, and that takes 240 times more. So there's quite a big speed differential here, and so there's obviously something very different going on underneath to account for that. And what's going on behind the scenes is this mysterious block manager object. So if we take a data frame and we do .blocks on it, we get back a dictionary where the keys of this dictionary here are all the different data types that are in the data frame. If the values of them are then other data frames that have all columns of that one type. If we get the block manager, which is an underscore data attribute of the data frame, and then look at the blocks in that block manager, we see that we have an integer block, a datetime block, and an object block. So the object block has all of the strings. So what actually Pandas has done underneath is taken a heterogeneous data frame where the columns are of different types, and it's partitioned them into subsets of columns that all have the same type, and then those subsets of columns can be represented by one numpy array. And that one numpy array is now homogeneous, and it has just one type, and so the types of indexing and selection operations that we saw near the start of the talk, we can do those on that individual block manager block. Now, there are various mappings between the numbers of the blocks and the columns come in there that's shown in the next one here. And by doing some timing, we can see that retrieving the different values from these blocks is closely aligned with what's going on here. Let's just... So just back to this slide here. So you can see that where we've pulled out no, sorry, I'll move on instead. Okay, so one of the other aspects of using the block manager to retrieve individual columns, and this is why getting the series was so fast, was that there is a whole lot of inbuilt caching going on, so that if you get a series over and over again, it's already cached the reference to that, and it can just return that immediately rather than figuring out again which columns of the table it is and so on. We can see that by getting the data frame in the REPL. The square brackets is really the double underscore get item method, and if we do in IPython or Jupyter a double question mark and then hit enter, that will then show us the source code. So one really useful principle with Pandas is if you don't understand what it's trying to do, then rather than calling the function to do it, put in the double question marks and hit enter, and then you'll see straight away what the code is being called. So if you do that, you'll get a code listing for the getItem function, and we can then trace through the layers of calls that it's doing, the getItem column, and then look at the values of that. And that will then show that there's, in red down here, a getItem cache. So this is one way that numpy, that Pandas uses to save redoing the same operations over and over again to make your calculations fast. And we can see how this works if we timing just getting a series from our data frame. The timeIt function in IPython realizes that the first run is relatively slow and subsequent runs are much quicker, and so it says, it suspects that some caching is going on. And we can look at the cache and see what's in there. If we run this again, we don't get that warning because it's already cached. So if we want to select some columns, there's two different ways that we can do that. In this example here, so getting the game number and the round, because we've got multiple columns in there, it returns a data frame, and that takes 500 microseconds. And that operation of retrieving that data frame is actually 2 individual steps. And the first step can be thought of as getting an indexer for those columns. And in Pandas terminology, an indexer is just an array with integer values that tells us which rows or columns to come back. So that does the lookup to translate these values into offsets or indexes into the underlying data table. And then the second step is to use that, these indexer with the take function. And we saw in numpy that there's a take function that's used to pull back individual columns, and so that's what Pandas uses. It can be a little bit confusing here because we're talking about index objects, we're talking about an indexer as an array of integers, and we could talk about an index into rows and columns. So it can be a little bit confusing, but specifically an indexer is an array of integers saying which items we need to take. So the result of that is a little data frame like this. When we are selecting rows from a data frame, relatively very similar thing goes on. In this case, it was specifying rows 14,837 to 39. Now, this is treated like in Python, where the ending point is excluded. This little note here says that if you use the iloc function, then you'll you'll include the end one. The timing for this is if we pull this out, we can do it in 120 microseconds, which is pretty fast. One thing to see is that the sub-data frame that we get from the blue section here, if we look at the columns on it and check how that relates to the columns on the original data frame, using the is operator, that comes back as true, saying it's the same object. So what Pandas has been able to do is they've been able to take a new data frame and stick an existing column index on it. So that doesn't need to be rebuilt from scratch. It just, a reference to that can be added, and so that's relatively quick. The row index for our new smaller data frame is also a range index object, and this is it knows that it has a new start and a stop, so it's been able to build that really quickly from the other one. So when we're thinking about what these selection operations are, they can be boiled down to looking up in the index, a row index or a column index, to see which rows or columns that we need, and then an operation to actually retrieve the right rows from the underlying numpy data. So here is some timings for doing different aspects of that. These examples here that are operating on dot values, the dot values gives a numpy array. So this is what you get at numpy speed, and then the extra pandas operation needs to add a little bit more to do the sort of decoration around the rows and the columns. So that's how the basic selection of rows and columns works. The next step that we would want to do for our analysis is to reformat columns and add some indexes to the rows. So the original data was from the perspective of a game that involved 2 teams. We want to get a set of data that is now from the perspective of teams. So each one of these games needs to be split into 2 rows. And we can do that by getting results from the perspective of a home team and an away team. And one really nifty feature of recent pandas is that they can split a string into multiple columns straight into a data frame on a regular expression. And so the home scores and the away scores section there is doing that into columns that are named G, B, and F for the goals, behinds, and then the points for. And then because we've got home and away teams, the points for one team is equivalent to the away points for the other team. This gives us two different data frames that we can then stack together with concat, and then we can put index on that. The end result of doing that is a data frame that looks like this. So let's just look a little bit more into what indexes are and how Pandas treats them. Here is an example of an index that is not unique because it repeats a value, but it is monotonic because they're in order. And so if we use the index to find out what locations an element is at, for an A, there's just one of them, so we get a scalar 0 back. And if there are multiple locations for it, then we can get a slice. This second case here, the index is no longer monotonic, and so when we ask the index to give the locations back, it gives us a Boolean array with trues and falses, with trues where the matching elements are. And if you think back to how indexing in numpy worked, the second last example we had indexing with a Boolean array, and that's what Pandas would use. This is how Pandas constructs that array to say which rows or columns to select.
Question, you might get to this in a second, but so earlier you were saying that an indexer is sort of a list of indices.
Yeah.
Is that what fundamentally Pandas is using to index, or is it a Boolean kind of thing where it's pick this index?
Well, it depends on the situation. So it tries. Pandas, if you look in the code in Pandas, has a lot of special cases for handling the different situations. If it can do things with a slice, the simplest possible way, it will do it with that. If it needs to specify individual columns or rows, then it will specify those. If it needs to have something that will cover the whole with a Boolean, then it will use that. So one of the other uses of indexes in Pandas, and this is really what it brought over from DataFrames in R, was using indexes to align series. And the way that this works is, here are two series where their indexes are slightly different. If we add them up, then down the bottom there, you'll see that we've got some nan values where there are some gaps where the addition didn't work. And also, it seems to have turned into floating point numbers. So what's actually going on here is shown on this side, is that in order to add these two series together, they need to have compatible indexes, and the indexes are made compatible by, first of all, taking a union of the indexes and then re-indexing the series. And that expands out the series or contracts it, leaving the values we need, putting in a nan where there are any gaps. Now, because nan is a floating point value, our array can no longer stay as integers, and it has to get promoted to floating point. So if you're doing some kind of addition of series or something like that in Pandas, and you suddenly see floating point numbers have popped up where you didn't expect them, it's because the index expansion, in order to match them up, has inserted nan values, and then so that's promoted your integers to floats. Another thing that indexes are used for joining and merging. If you have an old version of the slides, or one from before early this morning from my repo. This slide won't be in here. I added this first thing this morning. If we have two data frames and we want to join them, there's a simple join operation, the DataFrame.join, and we can do an inner join or a left join. And you can see if we do a left join, that's done that there are some values from the left index that are not there in the right index. So that's had to effectively open up a gap in the right-hand data frame where NaN values have been inserted. They've been promoted from ints to floats so that we can store a NaN so that all columns have the same type. So that's what the join looks like. That join is actually equivalent to using this function called merge, which has a whole lot of special cases of how to do these for different situations for data frames and series, etc., etc. The actual code for doing this is in Pandas, pandas.tools.merge, and it uses a low-level operation called a merge operation, and that will, in the middle of it, builds this object called a merge operation. Then you call get result on it, and the first thing it does is to figure out how the indexes of the left data frame and the right data frame need to be manipulated, and then what's the final index, join index, that gets returned. And then it does some magic about using those to concatenate the data from the block managers within those data tables and put it all together. So these are the infamous block managers coming out again. The left indexer and the right indexer are shown on the bottom left there. And the values that are -1, that's where NaN values will be inserted. So now for our data frame, we've added indexes to it, and we've actually ended up with multiple columns in that index, and that's called a multi-index. And some of the multi-index is here if we do scores.index. The multi-index has 3 parts to it. The first is the names, which is the names of the columns of the index. The next is the levels, which are the unique values in each of those columns of the index. And then the third are labels, which are integers that are used to as indexes into each of these levels. And so when Pandas is doing operations involving this index, involving multi-index, it first translates these different levels into numerical values, which it then uses to take back the different rows, and that's how we end up selecting rows using a multi-index. The values part here, this is a plain numpy array. These are all integers now, and so bringing back score.values, this takes 5 microseconds. Whereas at the start, when we had a heterogeneous data frame where the columns were of different types, that took 35 milliseconds. So this is 7,000 times faster because the data is just there. It doesn't need to be reassembled on the fly. We can look at what the data blocks are from within the block manager inside the data frame. And these are all integers, so we have just one block manager that holds integers. Now, what we want to do for building our ladder for the championship is to select some subsets of rows, and we want to take results just from 2016, and we want to take just results from the round robin tournament, which have round names beginning with R. We have other ones like the grand final, semi-final, and so on, GF and SF. but by selecting ones that begin with R, we just get the normal games. So that's the type of selection operation that we would like to do. Here are 5 different ways of doing it. One way that a lot of people that are new to Pandas use is to use groupby to get all of ones that are the same, say the same date and the same round of the tournament together, decide whether they want to keep them, and then use concat to put them back together as a data frame. If we do that, that takes 0.8 seconds, 820 milliseconds. This approach here takes 1.2 seconds. So this produces an array of the rows that we want to keep. This one is 8 milliseconds, so that's 100 times faster, which is looking up things directly from the index, whereas this is doing an iteration over the table. If we do an iteration over the table, then Pandas pulls back, creates a new series for every row in the table. So for the first row, it creates a table. For the second row, it creates a table. For the third one, for the second row, it creates a series. For the third row, it creates another series. That's a lot of overhead that it's having to do, where really we end up not using that. So that's very inefficient. Operating on the index directly is a lot faster. Here is another way that we could do it, where get the level values for a particular level, match that, get the level values for the round. So these are each arrays that end up being booleans, and them together, and then pull out the rows that match where that's true. So that's pretty quick. If you have a recent version of Pandas, you can actually do it directly like this, and that's the fastest of all. There's a note on the left saying that there's a bug in Pandas 0.18.0 where this doesn't work quite correctly, but that's all been fixed in 0.18.1, which came out on the 6th of May, and in 0.19, which was out last Saturday. Is that a question?
Tentatively, I'm just curious, what's the pattern that's getting expanded to get like from R1 to R9 there, like in the new sentence?
Okay, so this is just like a start and an end.
Okay.
So from a value to the next value.
And so there's like, in the datetime logic, it's automatically just matching the year.
So yeah. So Pandas will check the types here. Will say what's underlying here is a datetime object or a numpy datetime object. When matching on a string, it will then figure out what these strings mean in the numpy datetime terms, okay, and then use that for the upper and lower bounds to restrict that.
So that wouldn't work if you just gave it the year 2016. That wouldn't work.
If you give it the year 2016, that doesn't work. If you give the year as a number, it doesn't work. I mean, I have to say, putting this together, these look quite straightforward once they're presented to you, but to actually figure out exactly the right syntax for these, there's not necessarily one single place to go with good examples for exactly what you want to do, and Stack Overflow can often be a bit misleading because you see something that's several years old. So really, I find, and this is one of my, one of the things that means for me the Pandas learning curve is a bit like this, is it seems to involve a lot of trial and error at the command line, trying to get it exactly right.
From a management perspective at JP Morgan, how do you manage that learning curve when you have new people onboarding who are new to the Python ecosystem but you need to get stuff done? Well,
at JP Morgan, the way we manage anything for everyone is just throw them in at the deep end and they have to cope. Yeah. I don't have a good answer for that. I mean, we have thousands of developers working in a code base that I think has 300,000 source files. That's probably 20 million lines of code, with live pushes to production globally happening 24/7, and it seems to work most of the time. I hope no one from JP Morgan is listening. It actually works really well. Okay, so with the numpy example, for indexing, the very last bit on the indexing slide showed that we could assign values with a subset of an array on the left-hand side. Here we can do the same thing in Pandas. So we could actually take, say, select a selection of an array that we want to zero out. We could set 0 to it, and then this whole chunk of the array has gone to 0. So that can be quite useful if you are trying to initialize or nuke out a portion of a data frame that you don't want. Now, we'll actually move on a bit. I'll just skip over here. Okay, so the next thing we want to do is add some calculated columns to our data frame. If we take this subset of the data frame and then just try and add a new column to it, we get a warning saying that we have a setting with copy warning. And what is actually happening behind the scenes here is that our data frame Y is referring back to the original underlying numpy data in the scores data frame. Pandas is worried that we're updating Y, adding a new column to Y, or changing values in Y, but we may not be aware that this would change things in the underlying data table, data frame in scores. So we get a warning for that. And the way around it is actually to make a copy, make an explicit copy, so we get our own underlying data array to work from. Now, inserting a column is really, really fast. The timings for doing that are here, and the reason is that every time we add a column, it will create a new block manager, and that breaks the rule that says a block manager has all of the columns of a certain type. Because if we added that into that new column into an existing block manager, that would mean a whole lot of copying of data. So Pandas presumes that you'll probably want to add several columns at the same time, and so it defers consolidating them until you run a function on your data frame that actually needs them to be consolidated. And so then it will do that behind the scenes, and so this flag, the data is consolidated, would be true. And it actually has just one block in the block manager rather than two there. So inserting columns is really fast. And this is one of the things that you might think is relatively slow, so you try and defer it. But actually, pulling out a series from a data frame is blindingly fast because everything is cached. Adding a column to a data frame is blindingly fast until you start to do calculations on it, and then it all gets consolidated. Now, to complete our ladder for the scores here, we needed to add columns for the number of games won, drawn, and lost. So we have this column P for the number of games played. For the number of games won, we can do that by comparing the goals for and against. We could also, a number of different ways of doing it. The wins, is shown there. For the losses, we can use an eval function like that to get that. If we do this, we end up with some things that are not quite the data types that we would expect. And the reason for that is this expression for the wins. It ended up as a Boolean. I guess if we thought about it, we would say, yeah, we get Boolean rather than an int. So we need to force that back to an int. And then for finding the draws, most of them, this one with the lock is the first bit is selecting which rows we want to select, which is where the points for and against are the same. So that's where there's a draw. And we want to stick that in a column called D. And when we put a 1 there. The reason why that didn't work out is that where there were zeros, we'll get nans. So we want to put the fill NA at the end of that, and that converts the nans to zeros here. But because we had nans there, those end up as floating point. As we saw earlier with missing values get promoted to floats. So we need to force that back to an integer. And then we end up with a table that we like. And again, you can see as we add the columns, we have the different data blocks, and they can then get consolidated. So now we can aggregate things with group by and group by team and do the sum. Now, in one of the examples earlier, we're doing concat with a group by, and that was really slow. That took 0.8 seconds. Here's a similar example added in a second level for venue to make the difference a little bit more apparent. And here this is 233 milliseconds. Again, because what this is doing is it's building a whole lot of sub-data frames and then merging them again. If all we're going to do is to call a function like sum on it or something like that, then actually Pandas is smart enough to not have to rebuild all the individual data frames within it, and it can just do that using low-level internal operations by figuring out which rows are in scope, and so that ends up being 50 times faster. So that's a good thing to know. Here's a description of the bit of the internals of it, where it pulls out an object called a grouper and figures out the groups and then the indexes on all of that. Now the last thing we want to do is to add the points and the percentages to new columns, and then also sort this so that it has the best team at the top. If you do this with the Jupyter Notebook in my GitHub repo, then that is through to the end of the season, so it will show the top teams at the end of the season. Now, we'll just do a bit of tidying up the formatting and adding a rank to it, and the end result that we get here is exactly the same as the result from the Australian Football League website back in May. So we've achieved our end result. Here's the code that does that. And along the way, we've seen a number of aspects of Pandas. So what we've seen is that Pandas is a really powerful way of doing data analysis, but it tries really hard to be optimized. You can give it a simple expression and it will figure out how to do that. If you structure your data so that it ends up being done in an inefficient way, then it can take 1,000 times more than if you do it in the most efficient way. And the key to understanding why that is happening is from looking at the core to it. One of the best ways to build this kind of intuition for yourself is to explore data frame objects and these type of operations in IPython or in a Jupyter Notebook using the double question mark to pull down, see the source code that's being executed, and using the time it or profiling functions to do that. Also, don't be afraid to scale up problems that you might do on a small laptop to quite large problems. By being smart about how Pandas represents data, you can actually do quite large problems on one machine before you scale out to something that uses maybe Dask or a system like that for doing something in a distributed way. And most of all, don't be scared to look inside the Pandas code. Trial and error can be very frustrating at the command line. You can easily spend half a day getting very frustrated when just a quick look inside the code will help you see what path things are taking. If you want to play around with some of the ideas from this tutorial, here are some things that you may like to do. But that's the end. So thank you very much. I guess we have about 4 minutes left. So if there are any questions, feel free to ask, or maybe come up and talk to me one-on-one, and everyone else go off and enjoy the rest of PyData. Thank you.